Okay, good afternoon to all of you and welcome to all 150 participants from all over the world to the webinar Emission Reduction Potentials in High Volume Casting Applications brought to you by ASK Online Academy. I'm Thomas Glattes, Head of Business Line Management EMEA, and I'm excited about this webinar, which will offer you some key insights and possibilities on how to reduce emissions in high volume casting applications. First, I will go through some organizational topics. Your name and camera pictures will not be shown due to data protection policies. Questions can be asked via the chat functions on the bottom right screen of the webinar tool at any time, and we will answer them after each presentation. And the recorded version of the webinar will be made available. You will receive an email link after the webinar where you can access this. We will show the impact of the different solutions on each step of the foundry value chain. On this slide, you see illustratively the different steps of the value chain. Key emissions at the process step central processing, core production and storage, and core package assembling is volatile organic compounds, or abbreviated VOC emissions. And key emissions at the two last casting process steps is BTX, a mixture of benzene, toluene, and the three xylene isomers.
It's an honor for me to have the privilege to present you how we can reduce emissions with the Colbox technology without changing the whole process and without big investments. Polyurethane Colbox resin used in foundries are the results of a polymerization reaction between the formophenolic polymer content in part 1 and the isocyanate content in part 2. Polyurethane is a 100% organic carbon-based plastic which releases volatile products into the atmosphere and which, during the cast process, burns and emits polluting products. If all Colbox are defined in this way, it is possible to limit this emission. The best system for this at present time is most certainly the EcoCube Blue family. In order to understand how to limit the emission by playing on the formulation, we prepare this illustration. It explains what can generally be found in Colbox resin. The active and essential product illustrated in blue, so the polymer and some low volatile solvents, are not directly harmful, while in red, we can find solvents and additives with very low regulatory exposure limits. Residual phenol and formaldehyde monomer are also particularly dangerous products. In the formulation of EcoCure Blue, in opposite, all these red products have been removed or at least used in concentrations below the declaration threshold so that they are then considered as stress of impact not relevant by the authorities. If we look at the regulatory labeling of the Part 1 products on the market, we find the same symbol hazards, sometimes with the additional mention of flammability. Whereas the Part 1 of EcoCube Blue has no pictograms and there are no hazardous products to be mentioned under MSDS. This is due to its particular formulation and in particular to the fact that EcoCure Blue Part 1 contains less than 1% free phenol and less than 0.1% free formaldehyde. For sure, the Part 2 still contains isocyanate, which remains to be declared and labeled. In addition to the initial formula, renamed here EcoCure Blue Pure, the EcoCure Blue range is extended with solution with less than 0.01% free formaldehyde, called EcoCure Blue Ultra, anticipating future changes in legislation, or reformulated parts 1 to increase resistance to storage at low temperatures. That is the EcoCure Blue Ice. This family is in constant development with customized solution possible, and the forthcoming arrival of a second generation of product with even better technical performance. Okay. To understand where the emissions come from throughout the foundry process, we have created this small diagram. You can clearly see here two types of emission. During the mixing, shooting, and storage of the cores, the emissions come from the evaporation of the lighter products. It can be the volatile solvents, but also amine and release agents. Whereas during the casting process, the binder in the core is burned. There are evaporation phenomena, complete combustion, and forced combustion without oxygen, also called pyrolysis, where the most dangerous pollutants are produced. For example, BTX and NOx. So if we look now at the evaporation phenomena, there are already VOC-free formulation on the market, whereas recipe containing aromatics or TOs generates VOCs. However, phenol with a vapor pressure of 0.2 hectopascal at 20 degrees is a pure VOCs, and its occupational exposure limit of 2 ppm or 7.8 milligram per cubic meter demonstrates its toxicity. Phenol penetrates the body very easily by inhalation. EcoCureBlue reduced the release of phenol by more than 80% and thus greatly reduced the risk for workers. Sorry. Okay. The BTX, benzene, toluene, xylene, are formed during the so-called pyrolysis process. The thermal degradation of the polymer network during the pouring produces fragments, so-called radicals, which can react further, recondense into the sun, or evaporate. This process can be analyzed but never precisely predict because beside the binder play in addition temperature gradients, transport phenomena in the sun binder mixture, and so on, an at least so important role. This is why the correlation between laboratory results and what is measured in foundries are often poor and sometimes even contradictory. The results are very much influenced by the measuring method whose reproducibility or sensitivity rarely allows reliable results to be given. The results presented here and on the next slides were measured in the USA using a method called Woodstack, specifically developed by ASK, formerly Ashland, which is probably the most reliable method currently available. Each value presented in the slides is the average of a minimum of 3 gray iron casting tests. So we can see that the selection of pure solvents and the reduction of monomer or aggressive additives can enable to reduce slightly the BTX. But when the binder reactivity is optimal, we can often reduce the use of binder. And that has a much bigger influence on the reduction of BTX or other pollutant. We can see here that the reduction of only 7% of the binder can provoke 13% reduction of BTX. And that is the key message. The less organic material you will have into the sun at the pouring, the less BTX and other pollutant you will produce. And that is definitely the best way to reduce the emission. So another major advantage of the blue system is the reduction of phenol also in the pouring atmosphere. Here there is a direct mathematical correlation between the free phenol present in the sun at the pouring and the phenol we will find then in the air. Okay, the EcoCureBlue is often more expensive than the most of the other systems on the market. The reason is that the production time is a little bit longer because we have to remove the free phenol in a much drastical way. Furthermore, the solvent selection are much more restrictive than for the standard products because in order to optimize the percentage of use, we must be sure that the consistency of the quality of the binder we are delivering is perfect. But more than the price, the cost of use should be considered. And very often, the technical advantage offered by EcoQ Blue, so it can be binder reduction, substitution of sound, reduction of scrap, reduction of amine, can compensate the higher price. And on the top of that, all the EHS and environmental benefits makes the total cost of ownership of this product very often much more attractive than the standard systems. For example, reducing emissions or improving the working condition of your employees with less toxic products in the air is becoming more and more essential, even if it is not directly quantifiable financially. Another example, the reduction of the phenol content in the sun to be disposed of, on the opposite, has a direct financial impact. So that is some example of environmental benefits. As proof of the performance of EcoQ Blue, the wide penetration of the European market with more than 50 customers in some 15 countries. The EcoQ Blue is used in small and large foundries for small, medium, and large series in steel, gray iron, and lamellar iron, as well as in aluminum. Also, EcoQ Silver is more suitable in this case. All types of castings are produced with EcoQ Blue, from brake disc, engine parts, suspension and chassis product for cars or commercial vehicles, to casting for the mining, agriculture, rail, construction, or machinery industry. In all of these cases, the profits were able to compensate for the slightly higher price. It has been possible to reduce the percentage of binder by an average of 10% and at the same time reduce BTX emission by about 15 to 20%. One of the recent developments is the LFS technology, where different R&D teams have worked together to offer a solution to reduce formaldehyde emission from the stacks of the drying oven. By using EcoQ Blue LFS with Miratec LFS coating and Vano LFS additive, the customer has been able to reduce formaldehyde emissions from 20 milligram per cubic meter to less than the 5 milligram per cubic meter newly required in the revision of the TH Luft, the German law regulating atmospheric emission. This is a concrete example of a solution package developed by our different teams to solve new problems. And if you have specific problems in complying with certain emission limits, do not hesitate to tell us about your problem. We will involve the appropriate different departments to help you as best we can. Okay, EcoQ Blue is arguably the best cold box system on the market for reducing emission, but more than a binder, it is a new platform with which our teams are continually developing new solutions. In addition to EcoQ Blue, Pure, Ultra, and Ice, we have created the EcoQ Silver using aromatic solvents. Aromatic solvents are the best solvents for aluminum casting. They reduce the release of fumes and gases which condensate to form tars. EcoQ Silver is already in use at several aluminum foundries and even in some iron foundries. EcoQ Silver was then developed with TEOS solvent. TEOS, or tetraethyl orthosilicate, is an alternative to aromatic solvents. Both are VOCs, so highly volatile, and can enable to reduce tars. TEOS volatilize even faster than the aromatics and is less odorous when cold, and therefore is sometimes interesting. Nevertheless, TEOS is a less good solvent than aromatics. The properties are generally slightly lower, and the exposure limit for workers is about 10 times lower than for aromatics. So that is not a universal solution. We are also in the final stages of developing a second generation of EcoQ Blue, which will be even more efficient than the first and should be on the market before the end of the year. In parallel, we are working on a new solution for aluminum application, which will be a VOC-free solution, which unlike other blue solution, will generate less stars and will even reduce gas pressure well below silver aromatic or Theos solutions. If we look now at how its solution for BTX behave, silver and Theos, silver Theos are slightly better than the standard system as they benefit from the EcoCure Blue technology for their base. The new generation of blue will benefit from new solvents, specially selected by our R&D teams to generate the least amount of BTX, while a newly aluminum solution is, according to a first promising test, the system that will generate the least BTX. And all these systems also benefit from the performance of the EcoCure Blue technology, and in many cases, the binder content can be lower, which as explained before, is the best way to further reduce emissions. So the EcoCure Blue second generation will be even more reactive and efficient, allowing for further binder reduction and therefore a further reduction of emission and a further improvement of the total cost of ownership. The new aluminum solution will not only be VOC-free, but will also reduce gas pressure and be characterized by low thermal distortions. Okay, it was a brief overview on the promising solution that will come to market this year and which we will present to you in a much more comprehensive way in a few weeks or months. To summarize, the Blue family is certainly the best solution in the market to reduce its emission without important investment. We can reduce the emission and protect the health of the workers at many steps of the process by reducing evaporating emission in the core shop, but also at the point. Nevertheless, as long as we decompose an organic polymer at so high puring temperature, we will produce pollutants. With the Blue system, we can reduce the emission up to 90% in the core shop, while at the pouring we are more limited and can reach 25 to 30% of reduction in the best cases.
Thank you, Thomas. We will dedicate the last part of the webinar to ASK's inorganic binder system called Innotec. The binder system is applicable in hotbox core production processes and has set an industry standard as the emission-free alternative binder system in comparison to conventional organic binder systems, especially in the light metal automotive industry and low-pressure die casting and gravity die casting applications. The Innotec technology is described as a two-component binder system. Component 1 forms the liquid Innotec binder, which can be described as a modified solution of alkali silicates. The binder has a strong influence on specific properties of the molding mixture, for example, flowability, and the sand core itself. Characteristic strength profiles with adjustable humidity resistance properties result in dependency of the type of product used. Component 2 is the powdered Innotec promoter, which is a mixture of synthetic and natural raw materials based on a completely inorganic product composition. Through the use of the Innotec promoter, primarily mechanical and thermophysical parameters during the core production process, but in particular during the casting process, can be adjusted to assure castings of high dimensional accuracy and high surface quality. The main function of this component is to increase immediate core strength for fast ejection in the core production process. A typical molding mixture based on silica new sand is composed of approximately 2% of the liquid Innotec binder and 1.0 to 1.9% of the solid Innotec promoter. The higher the addition rate of the promoter, the higher the performance level of the product. The resulting molding mixture is fluidized by compressed air and transported to the cavity of the core box via a cooled shooting plate with integrated shooting nozzles. High diameters of the shooting nozzles and temperature control of the shooting plate are fundamental to assure high productivity in the production and sand cores of high quality. The shooting plate shuttles aside and is simultaneously substituted by the gassing plate. The core production is characterized by a physical chemical curing mechanism. The introduction and supply of thermal energy from heated steel tools and dehumidified heated compressed air leads to the evaporation of the free solvent water and simultaneously initiates a chemical polycondensation reaction with the formation of a three-dimensional silicate network that describes the actual strength composite of the sand core. The 100% emission-free footprint of the Inotec technology can vividly be demonstrated best by comparing the formation of fumes and smoke as a result of the thermal pyrolysis of the binder system upon casting or at the raw part in the process of permanent die-mold ejection. The left picture shows a polyurethane standard cold box bound core package after cylinder head casting directly at the ejection process of the permanent die mold. The formation of pyrolysis products visible by fumes and smoke leads to the necessity to implement exhaust air treatment systems. The picture on the right shows the exact same casting process with a slight but important difference that the Inotec technology is used. In comparison, the formation of pyrolysis products from the binder system is completely absent. The Inotec binder system is only dehydrated and converted to a glassy state by the thermal strain of the casting process and remains inside the casted cores. A gas chromatographic analysis of the emission stream shows that 98% of the emissions can be reduced. The main improvement here results from the absence of medium volatile compounds, which are responsible for BTX emissions in the casting process using polyurethane standard cold box binders. Besides the ecological benefit of missing emissions in the casting process with Inotec, savings in cleaning maintenance for the permanent die mold are a result as well. When casting with organic sand cores, the buildup of condensates occurs at the permanent die mold, which must be removed by employees in regular intervals to ensure correct functionality, especially of movable parts. The physical strain for employees involved in this work is high. In addition, there is a very high level of noise pollution. When casting with inorganic sand cores, this costly and energy-intensive cleaning step is reduced by more than 50%. As a side effect, permanent die mold casting processes with inorganic bound sand cores are operated at lower temperatures compared to casting processes with organic bound sand cores, leading to a higher die mold availability of 25%. Furthermore, the time-consuming cleaning of the air systems is no longer necessary. The use of hazardous substances in the exhaust air purification system is also no longer necessary. The figure here summarizes the comparison of CO2 equivalents for different binder systems in an automotive light metal foundry normalized to cold box for permanent die mold applications. The lack of dry ice usage in the cleaning process and the lack of energy consumption for air treatment systems in case of Inotec leads to a considerable decrease for the CO2 footprint for Inotec. Conventional hotbox binder systems based on organic components show an even higher CO2 footprint than cold box. ASK Chemicals commissioned TÜV Rheinland to create a comparative environmental life cycle assessment of a standard cold box binder system with Inotec in order to clarify which product is more environmental friendly through the respective life cycle. Overall, the inorganic binder system Inotec fares better, leading to the conclusion that Inotec is an eco-friendly product and is more environmental friendly than the compared cold box system. Besides the ecological benefit of missing emissions in the casting process with Inotec, an increase in productivity is apparent as well. The lack of condensate buildup in the permanent die mold for Inotec-based casting processes enables lower die mold temperatures, thus faster solidification results in addition to a higher permanent die mold availability because of savings in cleaning and maintenance. These effects overall contribute to a productivity increase of roughly 30% in the casting process at the die itself. An additional advantage of the inorganic binder technology, Inotec is embedded in its technological influence on the metallurgic structure of the casted aluminum parts. The metallurgic property of secondary dendritic arm spacing is mainly influenced by solidification. Thus, faster solidification leads to lower SDAS values and castings with higher mechanical strength. Lower permanent die mold temperatures in case of Inotec already provide faster solidification. But the residual water of the inorganic binder bridge further withdraws energy from the liquid aluminum melt for evaporation, leading to an add-on effect on solidification. Inorganic sand cores exhibit roughly 25% of the gas potential of organic bound sand cores. Thus, the pore percentage in the casting and degree of porosity is dramatically decreased. Both parameters contribute to improved dynamic properties of the casting as metallurgical structures of higher strength and elongation properties result. This effect enables wall thickness reduction and contribute to the overall trend of downsizing and lightweight construction, and especially in ICE powertrain applications. Traditionally, the inorganic binder system Inotec has been utilized in low-pressure die casting and gravity die casting processes to produce classic ICE powertrain components, for example 4- and 6-cylinder heads and the corresponding crankcases. Nowadays, Inotec has matured to a much more versatile binder system, which is applied to a wide range of aluminum passenger car components, for example e-engine housings, suspension parts, and body structures. The difference to state-of-the-art ICE powertrain applications is characterized by a different number of cores per core package and varying core weights. While ICE powertrain components are based on core packages with different cores of high diversity concerning mass and geometry, suspension parts and body structures casting processes are based on just 1 or 2 cores with greater mass. The versatility of the Inotec technology is achieved by segmenting the necessary product performance requirements of the binder system by the castings produced and by considering the total cost of ownership approach that captures the full cost structure of a casting process until selling the part to the respective customer. The determining key performance indicator here is the so-called sand-aluminum ratio that compares the weight of the sand core package with the weight of the casting. The higher the KPI, the higher the sand core weight and the lower the casting weight. ICE components, for example cylinder heads and crankcases, show a very balanced sand-aluminum ratio, while the ratio value is already increased for e-engine housings. Both casting types need in general binder systems that ensure high dimensional accuracy, as well as sand cores with a low gas potential and the very good shakeout performance of the cores, as both components use filigree water jet geometries. In comparison, suspension part castings are produced using voluminous sand cores. Thus, the sand-aluminum ratio is higher, and the main product focus changes to cycle time, strength, and core distortion, all parameters of the core production process itself. The following 2 slides will be used to demonstrate the effectiveness of this approach. A predominant problem in the production of cylinder head castings using inorganic binder systems is the appearance of sand adhesions and penetrations after raw part machining, especially on the core print areas of port cores. This defect is described by the partial appearance of sand grains on the casting surface due to the mechanical penetration of the liquid aluminum melt into the sand core surface, or the electrostatic adhesion of sand grains on the casting surface itself. Casting parameters, for example casting temperature and pressure, have an influence, but customers are seeking for a chemical binder system solution that withdraws the need for intensive process control and casting rework by shot blasting. In this case, ASK is able to fine-tune the performance properties of the Inotec promoter to the local sand quality used. As the components of both silica sand and the promoter are of inorganic nature, an interaction is commonly observable and changes the properties of the sand core, for example thermal stability. Thermal stability is described as the resistance of a sand core towards thermal and mechanical strain of the casting process, and is an intrinsic property of the binder system itself, characterized by the so-called softening temperature. The softening temperature of a binder system can be monitored using the heating microscope technology. The specimen on the left here shows a low thermal stability and is softened at temperatures below 730 degrees Celsius. The sample on the right exhibits a high thermal stability, and the specimen remains stable over a wide temperature range and is then softened outside the temperature of aluminum casting applications. The result of customizing the thermal stability of the binder system to the impurities of the local sand quality is that the defect of penetrations disappears and withdraws the need for cost-intensive shot blasting. The second example arises from the field of suspension part casting. The customer reported a limitation in productivity due to long cycle times and a reduced tool availability in the core shop. The current addition rate of the inorganic binder system was in principle too high, but necessary to handle the voluminous cores because of strength. The buildup of binder system residues on the core box surface and the core itself resulted in excessive use of release agent and tool maintenance work in short intervals. The solution here is to customize the binder system to the process by providing a binder system with an adjusted strength profile. Inorganic binder systems for suspension part cores need an adjusted strength profile in comparison to cores for cylinder head or crankcases. Higher immediate strength are necessary, lower final strengths are acceptable. As a result, the components of the binder systems could be reduced, enabling a cycle time reduction by 10%. In summary, the Inotec Trinity concludes the ecological, economic, and technological benefits of the binder system. Inotec is the emission-free alternative to conventional organic binder systems, more suitable and more environmental friendly. The initial higher invest for the equipment of core manufacturing is compensated along the process chain by savings in maintenance, the lack of air treatment systems, and the higher productivity at the die itself. Technological benefits rely on improved dynamic properties of the casting, enabling downsizing and lightweight construction. Inotec is able to reduce VOC emissions as well as BTX emissions by up to 98% along the complete casting process chain and is your industry standard for emission-free applications. With this said, I would like to hand over the presentation to my dear colleague to conclude the main messages of the webinar.
Christian, before I do that, there's a couple of questions for you.
Yeah, sure.
One question is, what is the current status of inorganic binder systems in iron and steel casting applications?
Well, serial applications for Inotec and iron and steel castings in Europe are still missing. We have understood that the casting temperatures of 1100 degrees or even higher remains a challenge for inorganic binder systems, as these materials act as a flux for silica sand. ASK has developed water-based coatings for Inotec-bound cores that overcome the sensitivity of inorganic cores towards humidity without core breakage. ASK is currently working with different industry partners with the intention to sharpen the requirement profile for the development. One concept includes, for example, the combination of Inotec forms, so outer forms in the package, and inner cold box cores in sand package procedures in order to reduce emissions and lowering the technological requirement profile for the Inotec forms at the same time. Other applications, like iron brake disc productions, rely on the use of 100% Inotec cores that are coated.
Okay, there's one more question. Can the Inotec technology and its benefits be translated from conventional to additive manufacturing procedures?
In principle, yes. Inorganic binder systems are applicable in the so-called binder jetting application. The liquid binder is applied via the printhead, and the Inotec promoter is included in the sand system that is built up layer by layer. In comparison to these conventional procedures using stainless steel tools with the core shooting process, the so-called printhead compatibility defines an additional requirement for the liquid binder for additive processes. The value proposition itself for Inotec as an environmentally friendly product remains untouched as the manufacturing procedures changed. The same is true for the productivity increase and the metallurgical structure benefits. ASK has managed to translate these advantages from Inotec to Inotec 3D, the inorganic binder system for 3D printing.
Okay, thank you, Christian. As mentioned before, any questions we haven't answered, we will answer after the webinar directly to you. Okay, we are at the end of today's webinar. We hope we provided you a good overview about the sources of emission along the process chain and the different potential solution approaches from ASK on how to efficiently reduce key emissions.